All right, it looks like we are ready to go live on our afternoon live stream here with Mr. Linford's class. We are going to go till about 3:20 unless people don't have any more specific questions, but for the next hour and 20 minutes, I'd like to review a couple topics from section 10.6, which was the division and rationalizing of radical expressions. And I'd also like to go over some topics from what we learned on Friday in section 10.2, and that was the topic of rational exponents. I plan on going over some problems from the exit ticket and some from the homework. We did a live stream earlier this morning where we reviewed other problems from exit ticket and homework, so feel free to go back into the videos and look at those later if you have other questions. But if you have any questions, feel free to let me know in the live chat. Go ahead and comment a question you'd like me to go over or any particular topics you'd like me to review. First up, let's go ahead and let's start with section 10.6. In section 10.6, we learned about rationalizing the denominator, what it meant to have a simplified expression or a simplified rational expression where either the top or the bottom of the expression have a radical in it. We said the big thing is you not allowed to have a radical in the denominator. So that was a big concept that we have to realize, okay, this is not a simplified fraction if it has a radical in the denominator. Now, the answer might not look as simplified, right? We can make the numerator as complicated as we want, but the denominator, the rule says is we cannot have a radical. So the first thing is we have to think, how can we go about and getting rid of this radical in the denominator? Really, the only way we have of changing around fractions is we can multiply the top and the bottom of the fraction by the same thing. That's really the only technique we have for simplifying a fraction or reworking the fraction. So we know we got to multiply the top and the bottom by something. So we're going to have to choose what we multiply by very carefully. The idea here is to multiply the top and the bottom by something that will create a perfect root. Gosh, I keep messing with my mic and it keeps clipping out. So the first thing that we need to do is understand what type of root is this that we're working with. This is a cube root. Now, since this is a cube root, we need to create a perfect cube under the radical. Right now, we have the number 3. Is that a perfect cube? No, it's not. So we're going to have to multiply 3 by something to get it to be a perfect root. Well, if there were 3 3's, then it would be a perfect cube. But right now we just have 1 3. So let's go around and change that. What if I include 2 more? That should work. And now I have y squared under the cube root. So if I had 3 y's, then I could make a group of 3. But I only have 2. So what would happen if I include 1 more? Well, let's go ahead and perform that multiplication, and let's do it to the top and the bottom. So we stay in proportion, and we'll see what we get. So the top just becomes 5 cube root of 3 squared y. And the bottom, I'm going to leave it in the radical for right now. The cube root of 3 cubed y cubed. So let's see what we get. Now the numerator, of course, we could simplify that to 9y in the cube root. It doesn't matter. And then the bottom here, the cube root of 3 cubed is just 3, and the cube root of y cubed is just y. So this is the way in which we're going to go and simplify down these expressions. Now again, the original and the simplified version might not look particularly simplified, right? But this is how we're going and defining it, making sure that the radical is no longer in the denominator. So the big goal is to think, what can I multiply the top and the bottom by so the bottom becomes a perfect root? Now, keeping on that idea, let's take a look at this problem. This is problem 4 from the advanced practice. In this particular problem, we have now a binomial in the denominator. So we have 2 terms that we have to deal with. So we just said on, I think this was Thursday when we reviewed this, we said, okay, you can't really go and just multiply by the square root of 3x, because when you distribute that through, the root 3x goes to the 4. Instead, we said, the thing that's really going to help us out here is the idea of the difference of squareds. We said if we multiplied a difference of squareds, we end up just squaring the first and the last term. And that got rid of the radical for us. So the vocab word we said was it's important to multiply by the conjugate. The conjugate is the exact same form to the expression except we change the sign. So I think I kind of defined it in the video for this section as the conjugate is the other factor in the difference of squareds. So if you have root 3x plus 4, the conjugate is root 3x minus 4. And what this is going to do is it's going to create the difference of squareds, and it's going to force the radicals to cancel out. So we'll see that in a second. First, let's do the numerator. 2 times root 3x, and then minus 8. Notice I'm distributing that 2 through. You do actually have to distribute the 2 through. A lot of times I'm still seeing people take 2 times root 3x, and then they're just saying minus 4. They forget that they have to carry it through to everything. Remember, this distribution really is, or I'm sorry, this multiplication really is distribution. We're going to be using it quite frequently. Now let's take a look at the denominator. So I'll do some work at the bottom here. The square root of 3x and 4 times the square root of 3x and negative 4. As we go and multiply these, we can see when we first have to multiply root 3x and root 3x, that's just squaring it. So we end up with 3x. On the bottom we have 4 and negative 4, so we end up with negative 16. Now let's take a look at the middle terms. This should remind us of the difference of squareds, because as we go and we multiply these terms together, we can see that these middle terms are going to cancel. We are essentially multiplying so we get the same thing except one's positive, one's negative, so they cancel out. In this way, we are forcing the difference of squareds to cancel out the radicals for us. It's a very clever idea. Something I really like teaching just because it's so interesting that this little random technique from factoring is exactly what we want in so many different instances, in particular here with the radicals. Now this is going to be our final answer. Again, is it any less complicated than original? Well, no, but in this definition of having a simplified fraction, meaning don't include a radical in the denominator, then it is. But don't worry, a lot of times students look at these and say, oh, my answer isn't any less complicated, or it looks more complicated or more messy. Don't worry about that. As long as the radical's outside of the denominator, we're good. Again, if you have any questions, please let me know in the live chat. If you have any comments or things you'd like me to go over a little more, let me know. But right now, I think that's pretty much all I wanted to cover for section 10.6, rationalizing the denominator. And now I'd like to go over a couple problems from 10.2. We're going to start with some from the independent advance, or the independent practice, and then we're going to get into the exit ticket. The first one I'd like to cover is problem 5 from the homework, the independent practice. Now, this should really remind us of the work that we've done with exponents and the properties of exponents. I think we did this back in Unit 1, and you might have seen it in other classes too, but when you go about working with exponents, whether they're fractions or whole numbers or with variables, the same rules apply. So what I'm going to do is I'm going to take this exponent on the outside, and I'm going to use the power of a product and power of a quotient rule to apply it to everything. Oh, Ahmed, you're asking if you can factor down the numerator or the denominator, do you? Are you talking about the last problem? If you can, yes. If ever, well, the only reason why you might factor down the numerator is to see if anything cancels, right? I would say if you should always check your work, so that's a good question. I would always try to factor down the denominator if it can. Obviously here it can't, there's no GCF or anything. But if there was, I'd try to factor that out and maybe try to factor this out as well. If you notice a couple of the problems, in particular for this one on the exit ticket, There are some problems where you can simplify by pulling a GCF out from the numerator and the denominator and having them both cancel. So I would check that. For the first problem, so this was the first problem we did for 10.6, but I think you might be meaning this is the first problem for 10.2. But the thing I would definitely say is, yeah, really, it's best to check your work by first factoring the denominator if it can, and then factoring the numerator if it can, and seeing if anything cancels. Sometimes it will, sometimes it won't. Majority of the time it won't. Maybe 30% of the time it will, 70% of the time it won't, I'd say. So yeah, for a problem like this, I would try to see if anything could factor, like especially if there's GCFs at all. Let me know if that clarifies. I still have that 30-second delay where you type something and then it actually comes through for me to see. Or actually, you type something, I see it, and then for me to respond, there's that delay. All right, but going back to this problem, I'm going to use the power of a product and power of a quotient. We said if you have an exponential expression, or any type of expression, right, and you have an exponent on the outside, you can distribute. It's not really distribution, but we said you could think of it that way. It's really applying the external exponent to each term in the parentheses. This is kind of like the distribution property. So I'm going to go through and apply it to each one. So we have x to the 3m to the 1 over m power, y to the 2m to the 1 over m power. And on the bottom we have z to the 5m to the 1 over m power. Now, we're going to now go through and simplify each one of these down. Using the power rule, right? When you take an exponential expression to an exponent, that means to multiply them together. So x to the 3m times 1 over m should just be x to the third, because the m's cancel. Then we have 2m times 1m. That's just a 2. The m's will cancel. Z to the 5m times 1m. Let's see, the m's cancel, and we're left with z to the 5. So that should be our final answer. Again, we're using just the exact same rules that we did with exponents, except instead of giving you whole numbers, now I'm giving you stuff in terms of fractions. Let's keep this idea going of using the rules of exponents in a little more complicated problem. Here's problem 7 from the independent practice. You'll notice we have two expressions, two separate expressions, each one of them having their own exponent that they're raised to. Well, the power rules, all the different versions of it, the power of a product, power of a quotient, whatever, said that you can take those exponents, those external exponents, and apply it to each of the terms. So I'm going to apply the 6 to x squared and y to the negative 1/3. And then I'm going to apply the 2 to x to the 1/2. I'm going to apply it to the y and z to the 2/3. Now, as I go through and apply each thing, I have to go and multiply the exponents together, because that's what the power rule says. So, x squared to the 6th power is x to the 12th. Y to the negative 1/3 to the 6th power is y to the, well, let's see, that's negative 6 over 3. But that just simplifies down, doesn't it, to negative 2. So hopefully you're seeing that several of these are actually going to simplify. Like this will become x to the 1st. And then we're going to end up with z to the 4/3. So you can see how some of these fractions actually go and simplify down. Now, we've done one step. We've applied that exponent to each thing, right? We applied the appropriate exponent to each thing. Now what we have to do is see if we can simplify or combine any of these like terms together, any of these variables together, and if we can simplify any of them. First thing I'm seeing, there's that negative exponent. I hate negative exponents. Let's start working with that. So x to the 12 over y squared. Remember, negative exponents mean you write the term that the negative exponent is attached to the opposite side of the fraction line. And then we're multiplying that by x to the first, y squared, and z to the 4/3. Now, let's go ahead and combine some of these together. X to the 12th times x to the first is x to the 13th. I have a y squared on top and the bottom, so those will just cancel out. And we're left with z to the 4/3. Now I think in the directions I said, make sure that you're writing all of your answers in terms of radicals. I want you to be comfortable going back from radicals and rational exponents. So, since I see a fraction exponent or a rational exponent, I'm thinking we're going to have to turn this into a radical expression. Now, one thing I need to point out. First off, as a little side note, the only thing that has a rational exponent is the z, right? So only the z will be in the radical. The x to the 13th has nothing to do with 4/3. Has nothing to do with the rational exponent. Rational exponents only affect what they're immediately touching, just like I said in the exponents unit. Exponents only affect what they're immediately touching. So for example, 6x to the 1/2 power. This is something a lot of times students would say, that's the square root of 6x. And that's wrong. That's not true. What it is the square root of x times 6. You see, the exponent only affects what it's immediately touching. So here, in this red example, the exponent was only touching the x, not the 6. In this problem, the exponent is only touching the z. So let's go back to this problem, and let's try to make sure, one, that we're only applying the radical to what we need to, the z, and we're making sure we're applying it properly. So as a little side note, z to the 4/3. When you're working with rational exponents, the denominator is the root, and the numerator is the exponent. So in this situation, we know that we are taking z to the 4th power, and we're also taking it to the 3rd root. Now, a lot of people ask me sometimes, well, wait a minute, Linford, wait a minute. Do we have to have the situation where the 4 is under the radical, or should we put it outside of the radical? So, for example, let me clear some space here. We have this situation, z to the 4/3. Is that going to be the cube root of z to the 4th? Or is it the cube root of z and that whole thing to the 4th power? Which of these is the proper notation? Well, actually both of them are the exact same thing. Generally speaking, we prefer this one just because it combines everything together, while this one, you can't really particularly add or subtract. You would have to move it in before you start simplifying things down. And this makes the second version makes it a bit more difficult to simplify. So both of these are technically correct, but we prefer the first one, where the exponent is inside the radical. And the reason for that is when it comes to simplifying. So let's actually go and try to simplify this. Because we have the cube root of z to the 4th. So we can actually break that down even further. So we have x to the 13th by itself, and then we have the cube root of z cubed and the cube root of z to the 1st. So if I have 4 z's and I need to make a group of 3, okay, I have a group of 3 there, and I have 1 by itself. So the final answer is x to the 13th. The cube root of z cubed is just z, and then the cube root of, there we go. The cube root of z cubed is just z, and the cube root of z just stays as itself. Let me know if you have any questions on this, right? We're moving several steps at once here. This first part should be fairly simple, right? Just getting to this component of x to the 13th, z to the 4/3. That's really just using the rules of exponents. So hopefully that part's making sense. But the next part, where we have to take that rational exponent and convert it back to a radical, is the part that we really want to make sure we practice and understand. So let me know if you have any questions. Again, comment them in the live stream. Let me know if there's anything I can review or go over for you. But with that, let's go ahead and jump into the exit ticket. I'd like to go over problem 2 in this video from the exit ticket. I went over problem 1 earlier this morning. You can go back and take a look at that video if you'd like. But right now I'd like to go over problem 2, and then we'll go over an example of problem 1. This problem in particular is something we've been taking a look at, where we see we have an exponent or an exponential expression raised to an exponent. So we have this whole term here raised to the 1/4 power. What we should do in this case, and we talked a little more about this in the earlier morning live stream, but there's really always 2 options. The first option is you can try to simplify the inside first and then apply the exponent. Or you can just go and apply the exponent first right away. In this case, nothing can simplify on the inside, so let's go ahead and apply the exponent through to all of the individual terms. So we're going to take 16 and we're going to raise it to the 1/4 power. We're going to take x to the 5th and raise it to the 1/4 power. And then we're going to take y to the 3/4 and raise it to the 1/4 power. Okay. That's 16 to the 1/4 power. X to the, well, if it's x to the 5th to the 1/4 power, that means we have to multiply them together. So we get 5/4. And then here we have y to the, 3/4 times 1/4 is the 3/16 power. Okay? Hopefully this is making sense. Again, this is just the rules of exponents that we've been working with before. Let's go ahead and start simplifying and maybe converting things into radicals, okay? 16 to the 1/4 power. Hopefully we got our fourths started to get, or we're starting to get our fourths memorized, but the 4th root of 16 is 2. And then here we have the 4th root of x to the 5th, and we have the 16th root of y to the 3rd. That's what both of these the rational exponents are saying. The first one should be fairly obvious to us that we can simplify it down, while the second one here should be obvious that we can't simplify that down. In the first problem, or the first radical, we have x to the 5th, and we're trying to make groups of 4. So I'll take 4 of the x's in one group, and I'll leave one of them to the side here. Now when it comes to this term, I only have 3 y's. I'm trying to make groups of 16. So that's not really going to work out. So I'm just going to have to leave the 16th root of y cubed to the side here. That's not going to break down, and that's okay. I don't always expect things to break down. So we have 2, and the 4th root of x to the 4th, that just simplifies to an x. And then we're left with the 4th root of x. And the 16th root of y cubed. Now here's the issue. We don't want to have the 2 radicals there. I mean, it's not that big of a deal, but it's much nicer to actually have them combined together into one radical expression. So what I'd like us to do is to take a couple minutes to go through and break down how do we combine these 2 radicals together. Now, if you remember back to when we were multiplying radical expressions, we had this idea about changing the index and the exponent of the radicand so that you keep things in certain proportions. Well, that was fine, and hopefully that made sense, but it was a little kind of convoluted, a little kind of hard to visualize at times. It's a lot easier to visualize with this idea of turning radicals back into rational exponents, so putting them into exponential form. So what I'm going to do to the side here, we have the 4th root of x. That's x to the 1/4 power. And then we have y cubed, or the 16th root of y cubed. So that's y to the 3/16 power. Just like we had before. But this time, I want them to be under the same radical. That means they need to have the same index. I'm taking the same root of each one. But notice I have different roots. That's the 4th root. That's the 16th root. So to get them to be the same roots, I need to get them to be the same denominators. So how could I change 1/4 to have the same denominator as 3/16? Well, hopefully people recognize that, well, that's actually a very simple task. Multiply the top and the bottom by 4/4. If we do that, if I multiply the top and the bottom by 4/4, we are going to get x to the 4/16 power times y to the 3/16 power. Notice that x to the 4/16 power is the same thing as x to the 1/4 power. These are the exact same thing, okay? It's just a less simplified version. But now they both have the 16th root. We're taking the 16th root of each one. So we've gone and we've changed the index. We didn't really change the expression, we've just changed the index. So we have x to the 4th, y to the 3rd, both of these to the 16th root. So that's what in the box, what the red box really simplifies to. So let's try to sub that in. We have 2x times the 16th root of x to the 4th, y cubed. These expressions are equivalent. These expressions are equivalent. What we had originally and how we just combined them together, okay? Again, exact same things. We could split it up, and if we split these up into the 16th root of y to the 4th and the 16th root of y to the 3rd, you get these back, okay? It's just we're trying to combine things, to use our properties to really combine things together to get it a little more simplified for us, okay? Let me know if you have any questions on this. I had a student ask me to specifically go over these exit ticket problems, especially something like problem 2. So let me know if you have any questions about this, how we're going and simplifying it. I think this part, getting to here, is fairly obvious. I think getting to here is where it gets a lot more confusing, where we have to really use these ideas of rational exponents to combine things together, okay? Again, I'm going to put this video, I'm going to post it on YouTube once I'm done with the live stream, so if you want to go back over anything or review any of the problems that I did, feel free to watch the video once we're done. You can also go and see the first live stream we did earlier today. And again, let me know any questions that you have. Feel free to comment them in the live chat. Let me know if you have any questions, and as we go forward with these live streams throughout the semester, feel free to email me any particular topics you'd like me to go over and review, okay? Really, these live streams are for you. I just picked some problems that I think people might like to go over and review. If there's anything you want me, you want to direct me towards reviewing or explaining more, feel free to just let me know. Let's go ahead and now try an example problem I came up with that's very similar to the exit ticket the first problem in the exit ticket for 10.2. So here we have two expressions being multiplied together, and we notice that the expressions contain rational exponents. So as we go through, this is going to use a couple of the rules of exponents that we need to remember. One is the multiplication of like bases. So right away, we can reorder this multiplication so that we're multiplying the numbers and we're multiplying the variables together. So this is just reordering the multiplication. 4 times 5 is the 20. And then x to the 1/3 times x to the 4/5. Here we have like bases, they're both x's, but we need to add the exponents together. So that was the rule of multiplication of like bases, add the exponents together. You could go and do some side work and actually figure out what's 1/3 plus 4/5, make a common denominator. I'm just going to cheat and put it into my calculator. All right, so I typed in 1/3 plus 4/5 using parentheses, and then I'm going to convert that to a fraction. So I get 17 over 15. So we have 20x to the 17 over 15th power. Now, I believe in the directions for the exit ticket, I told you to actually go ahead and write these as radical expressions. Don't have any fractions as your answers. Convert them to radicals. So let's go ahead and let's do that. Remember, The only thing that's going to have a radical is the x. 20 has an exponent of 1. It has nothing to do with the 17 over 15. So the only thing that's going to have a radical is the x. Make sure of that. So let's convert that to a radical. The root is going to be the denominator, 15. And the exponent on x is going to be the 17. So I have x to the 17 to the 15th root. So can I go ahead and simplify that? Well, one of the tricks we said was, yeah, if your exponent is bigger than your index, you can simplify it down. And hopefully that's getting pretty obvious to us right now, that we can rewrite this. If I need a group of 15, well, I can take 15 of the 17 x's I have, and then I can just take whatever's left over. I think that'll be 2 x's, and I can break this down. The 15th root of x to the 15 is just x. And then we have the 15th root of x squared. So this is going to be our final answer. Again, all that we're doing here is really using the rules of exponents, the multiplication of like bases, to get to that step. And then we just convert things into radicals to simplify it down. To really simplify things down, get comfortable switching back and forth between rational expressions and radicals, okay? You can see in this problem, all I had to do was I just had one thing raised to a rational exponent, so I just had to convert that to radicals and simplify it. In the previous, in the previous problem, we had two expressions, right? Two separate expressions raised to different radicals. So that's why we had to convert it and simplify it in the fraction exponent form and then get back to radicals. So this process is likely if you have two separate radical expressions. But here, we just had the one. Okay? That's really it for me, as I'm losing my voice right now. Perfect timing. This was really the only problems I wanted to review, or I thought of reviewing. If you have any questions, let me know, or anything more you'd like me to review. Otherwise, we could end this live stream a bit early and allow people the opportunity to go back through, look over some of the things that we talked about in this video, and check out some things that we did in this morning's live stream. You can, of course, email me any questions you have to klinford, that's KLINFORD, at wccnet.edu. And feel free to check out the website linfordmath.weebly.com. There's where I'm posting all of the videos for each section. Today I actually have posted the practice test, so you should be able to go through and work through essentially all of those questions and check over your answers, make sure you're doing them correctly. The test will go live tomorrow morning at 9 o'clock on EdgeElastic. At linfordmath.weebly.com, I will actually have a link to EdgeElastic posted under the Unit 5 assessment section on the unit tab that we've been working through, or you can just log into EdgeElastic. You'll have about a week to do it. That's all that information is listed on the assignment sheet on the Weebly webpage. If you have any questions, again, let me know at klinford@wccnet.edu. Let me know any comments you have. Feel free to post them below, but if you want a quick response, go ahead and shoot me an email. And with that, I think we'll bring this live stream to an end pretty early. I will be having another live stream starting Wednesday at 9 a.m. Let me know if you have any questions. I have some office hours available later today. You can go into the Contact tab at linfordmath.weebly.com to schedule that. And we can go over any problems that you have, but starting Wednesday, 9 a.m. is going to be our next live stream. So if you have anything in particular you want me to review, let me know. Until next time, take care.